Hi guys, so I'll give you a quick talk on 10.2, which is kinetic and potential energy. So this is 10.2, and the objectives that I'd like to cover in this talk are what happens to the work done on an object when it's lifted, what energy changes takes place when an object falls, and what happens to the kinetic energy of an object if its speed is doubled. So, start off, I just want to look at if we wanted to go about working out what is the energy of a moving object, how might we do that? So, I mean, energy of a moving object. Let's look at SUVAT. So we've got SU, V, A, and T. Let's just say it starts from rest and goes up to a certain value. So we'll just call that U. We'll call it final value V, and we've got S, A, and T. Let's just see. We'll see what comes out. So let's use the equation work done equals force times distance. Now our force equals mass times acceleration because F equals ma. So we need A from SUVAT. We don't know what that is. So let's see what we have. And let's also look at what S is. So there's an equation for S, because we'll substitute S in for D, because distance is just S in our equation. So we've got what force is, and let's see what S is. Well, S is just, if we don't want to use A, because we don't know what that is yet, let's use a half U plus VT. U is 0, so that just equals VT over 2. So that's our distance travelled, VT over 2. And what's our force? Well, we need acceleration. So what's acceleration going to be? Well, we can use V equals U plus AT. U is 0, so A equals V over T. So force equals mV over T. So putting that together, we've got work done equals our force, which is mv over T, multiplied by our distance, which is v T over 2. So that means our work done, or our energy, is half times m times v squared, which is what you know as kinetic energy. So that's where it comes from. So I just wanted to show you that. So that's where we get kinetic energy from. Just by using SUVAT, F equals ma, and work done is force times distance. And it might be worth mentioning here what happens to the kinetic energy of an object if its speed is doubled. Well, if we've got energy equals a half mv squared, and now if we're substituting 2v, energy equals a half m 2v squared. Wrong, 2v squared. So this was E1. Now our E2, which is because we're putting 2v in, so E2 is going to equal a half multiplied by the 2 squared, which is 4 mv squared. So E2 is going to equal 2 mv squared, which you can see is 4 times E1. So if you double the speed, you get 4 times energy. That's why speed limits are so important. Oh, looks like I've got a random picture just sticking here. I don't know why that's there. Apologies about that. So that picture should actually be up the right, but it doesn't matter. I can talk about it here. So we've got what I want to say about this one here is sometimes we've got problems where we have to talk about the increase in gravitational potential energy of an object. I can talk about it here actually. So, so if we're in a gravitational field, so these lines are just showing the direction that a mass would fall. We do more about this in year 2. And if we have got an object that is moved through a distance that is at a distance above a set height, in this case it's the surface of the Earth, or this is the ground, and this is a distance h. So we still use W, work done is force times distance, but in this case force is mg and the distance is h. So this is where gravitational potential energy comes from, because the force is equal to mass times g and the distance is equal to the h. Now it's worth saying here that you can fix your 0 point of h wherever you want. And what do I mean by that? Oh, someone's saying hello. So you can fix your 0 point wherever you like. So our h is from the surface of the Earth. Now, if we were to do a question about a pendulum, here, say the surface of the Earth, no, you're doing it above a table, or you're above the floor. So here's the surface of the Earth. You can set your h equals 0 value here. And then when the pendulum kind of goes up to here, I don't know, this being h equals 2, for example, say the high h equals 3, the highest point, then so if that's h equals 3, like the highest point, then it's just a difference between the two heights. And because we're doing a change in height, because up here is actually GPE equals mg delta h, because it's a change in height, you can set your 0 wherever you like. Now, when we've got a question like a fairground ride, sometimes they say things like excluding friction. So it might convert all of its kinetic energy at the bottom here, you can't see that, at the bottom here, into GPE at the top here. So all of the kinetic energy might go into GPE. Well, in that case, you've got a half mv squared equal to mgh. And the m's would cancel there, so you'd have a half v squared equal to gh. So then the maximum height that roller coaster could be, which is the maximum as in if there was no friction, but if there is in real life, would be equal to, so the maximum height would be equal to v squared over 2h, or another way of looking at it, min speed to get over that would have to be equal to root 2 gh. So it's quite a useful equation. That's only if they're neglecting friction. This worked example here is not. So it's on a fairground ride. The track descends by a vertical drop of 55 metres over a distance of 120 metres along the track. A train of mass 2,500 kilograms on the track reaches a speed of 30 meters per second at the bottom of the descent after being at rest at the top. Calculate the loss of potential energy, the gain of kinetic, and the average frictional force on the train during the descent. Now, let's have a look here. So let's just do something fancy. It doesn't really matter what it is. It gets to the bottom. You could have a picture like this. This is what most people would draw. It doesn't really matter. What do we know? On the fairground ride, the track descends by a vertical drop of this. 55 metres. So this distance, the track length is 120 metres. At the bottom, V is 30 metres per second. And its mass is 2,500 kilograms. So, loss of potential energy of the train. So that will be how much it had at the top, because obviously it's going to have to lose it all by the time it gets to the bottom. So, what is A? So that's GPE. Is equal to M times G times change in height. So 2,500 multiplied by 9.8 multiplied by the change in height, which is 55. And that's equal to 1.13 times 10 to the... Oh no, 1.35, sorry. So 1,347,500 is equal to 1.35 times 10 to the 6 joules. So that's how much it loses by going down. Now, how much of that is being turned into kinetic energy? Well, kinetic energy is a half mv squared, which is 0.5 times 2,500 times 30 squared. And that's 1,125,000. Just to subtract these, use their actual values. So 1,347,500 was the original amount. So actually, the amount lost, if you subtract the 222,500. That's how much you've lost. And as you know, work done is force times distance. The question is asking for the average frictional force. So we have to do force. This is part C now. Force can be work done over distance. So that's 222,500, and thankfully they're giving us a distance over 120. Which will kind of give us energy loss per metre, which is force. So, which is equal to 1854 newtons. So, hopefully, in this lecture you've learned you can answer the questions: what happens to the work done on an object when it is lifted, when it goes from its store into gravitational potential, what energy changes take place when an object falls, when it goes from gravitational potential into kinetic, what happens to kinetic energy in an object if its speed is doubled. So hopefully they're all answered for you. And any questions, please put them in the comments.